Thank you, BC Forage Council, for inviting me to speak. Soil water is actually something I work extensively on in one of my previous career steps. And I'm just sharing, and I hope you can see that the presentation. Is that okay? Yeah, you can hear me.
That looks great.
Good. So yeah, without further ado, I have a lot on the plate here. I will get started. And as Serena mentioned, I will have 2 or 3 polls during the presentation and 2 or 3 breakout sessions. But those breakout sessions, be assured, won't be any homework or so. It is more a real breakout where you can take a break and maybe ponder about the question I'm going to ask you when we come back, so you won't be quizzed on it. So, well, maybe you want to start that we're living in a maybe temperate rainforest, but actually when you look at that here in BC, we have really extensive droughts in summertime. So water is really not something we can take granted in BC. And I want to share with you here what is called the so-called soil plant atmosphere continuum. And there are a few things that I find is interesting, and what I want to share, point out here is there are some. One of the interesting thing is that only 15 to 60% of actually the water that touches the soil, if you want, or is coming with precipitation or irrigation, is actually reaching the plant. And that is a wide range, 50 to 60%. So some of those losses can, well, they can be managed. Some are more difficult to control. So we can control things like runoff. Sometimes, depending on the topography, we can reduce that to almost 0%. Other phenomena like interception and evaporation depend a little bit on the management of our crops. There is so much we can do, but even here, there are ways we can improve these losses. And finally, we look much more in detail is how we can actually change the storage capacity of our soil. So maybe let's get started. We all know that picture. It's a rainy day, and then it's soaking wet. And after a while, the water, well, it's ponding, and then it's getting less and less on the surface, and it's draining away. But there is still some water left in the soil, luckily. So the question is now, what forces are actually moving the water in the soil? And that is actually already the first time I want you to kind of maybe we won't make it a breakout room, just maybe think about for a minute, and I'll pause here. What do you think are the forces that actually move water in the soil? I'll give you 1 or 2 minutes. Serena, no need to make a breakout room here that early. Maybe just think about that. What do you think moves the soil, the water in the soil? So I want to start with the easy one, and that is gravity. So gravity is something that we all agree moves water from top to bottom. And this is what is defined as the gravitational potential of the water. That occurs predominantly when all pores are saturated, and that makes water flow from top to the bottom. But it doesn't really explain that, well, when we see water flowing through or percolating through a soil profile, it doesn't really explain, while once that water has moved through the soil profile, while there is actually still some water left. So we see it's moving slowly down along the profile, and depending on how dry the soil was before and other properties, this water will be absorbed by the soil or will ultimately go into lower layers. Well, to explain what actually keeps the soil back, we will need to know that soil is, well, water has two charges, has a negative and a positive pole, if you want, and that contributes to phenomena that are called cohesion and adhesion. So cohesion is the attraction of the water molecules to each other, whereas the adhesion is the attraction to solid surfaces. And those solid surfaces can be in the lab, it would be a glass tube, or in the soil, it is the surface of a soil particle. Now this force, you can see that when you take some water and just pull it away, what is between your fingers, well, this is the adhesion. And what keeps actually water together, that would be the cohesion. And this gives, well, this is the origin of what is called the capillary rise. So when the smaller the tube, the diameter is, the more there are forces that actually pull, or the ratio of that surface that can pull, let's say compared to the ratio or the weight of the water column, is favorable to the small surface. Now, as bigger those tubes become, or the pores become, well, the ratio becomes less favorable for the surface. So now the water column becomes heavier and heavier, and then the water can't rise that easily anymore. What does it mean in the soil? Well, the smaller pores do rise the water more than the larger pores. Now, in our in a soil environment, when you look at something really coarse like sand, sand has a lot of really large pores, which can allow water to move quite quickly, but then the water doesn't rise very high in those pores. So that means it does rise in the beginning much quicker than more fine textured soils, but then it levels off very, very early, within a few minutes, or yeah, even sometimes seconds. This is quite different when you have something really fine textured. This takes a lot of time, but it keeps on climbing, keeps on climbing, keeps on climbing. So there is a rule of the thumb, just leave it for your information, that you can actually estimate the height of the rise by dividing the radius of the pores, the ideal radius, by when you divide 0.15 in centimeters by the ideal radius, just to give you an idea. That can give sometimes for smaller pores mind-boggling heights. Well, but in reality is there are no let's say perfect pores that are straight and where the water can climb. And so we in the soil, we therefore divide this, when it comes to soil water, the soil profile in 3 zones. One is the zone that is always saturated, which is the phreatic zone, which is always wet. And then the one on top, the vadose zone, is the one that is more or less unsaturated. So there's little water in that zone. And the capillary fringe, that's the one that is actually where there's a purely the gain from saturated layer. So here we observe water coming not from the top, but rather from the bottom. And that depends really on how coarse that is. For sandy soil, we're looking at something like 15 centimeters. For something more loamy, 30 centimeter. If you have really a very fine textured soil, that can go further up, 50, 60, sometimes 1 meter. Now, this capillary rise might be a little bit misleading because it's not only a rise, it goes all the ways. So it goes up to the sides and everywhere. And maybe here a small pool, the first pool. I want you to figure out, you see here those different soil profiles. And so you see the one is the loamy sand, something a little bit coarser, and then you have the clay loam, which is a little bit finer. Now you see to the right top, there's a fertilizer band, and on the bottom is a drainage pipe. So I wonder whether you can just, in a pool, figure out which of the ones, the loamy sand or clay loam, where does the water reach the fertilizer band first? And Serena, if you don't mind just pulling up that first pole. So 20 plus 6, that makes 26. So end pole. and let's share the results. So most are, say, the loamy sand, and well, a few say the clay loam. Let's see what happens in the soil. So we have that, just click here. So let's say we have, well, the water starts to percolate, right? So after 1 hour, you see the water is going down in loamy sand, and the clay loam, well, it's a little bit slower. Now, after 2 hours, the loamy sand, well, it goes even further, but you see now in the clay loam, that water is a little bit distracted to the side. It doesn't go that quickly, but it's going to the side. After 4 hours, well, the clay loam has already reached the fertilizer band. And finally, after 12 hours, the water has reached the loamy sand. Well, but the clay loam is still behind in depth, but in the width, it has reached the fertilizer band. And these are capillary forces that pull the water in all directions. So the winner for that question is basically the clay loam will reach the fertilizer band first. Now, this attraction can be measured in the field, and Mike will perhaps talk more in detail about that with an instrument called a tensiometer. I have a tensiometer here in the room, but I think with the background you cannot really see it. But basically, it consists of 3 parts. There is the porous tip, it's a ceramic tip, and that mimics the porosity of the soil. And then you have a tube. Typically, it's a transparent tube that you fill with deaerated water. You don't want to have air inside because it compresses and expands. So that's not something you want. And then you have a gauge that measures actually the vacuum inside that water column. And the vacuum comes into being when the soil tries to pull out that water out of the ceramic cup and connects with it and pulls it out. And this is depending on the strength, the metric strength, or if you want, the capillary forces of the soil. Now, texture is in a soil, of course, you know, there is not just one texture, and especially in formerly, let's say, aquatic environment, whether you have a lake or if you have some alluvial deposits, you find stratification of different textures. And I give you an example. Typically, well, it makes perhaps sense that when you have a sand soil and then you reach that impermeable clay layer, that well, the water stops and starts to not move very quickly anymore until, well, the clay kind of sucks that water out of the sand. But actually, it goes both ways. So when you have a clay layer and now you have a sand layer, so you have that abrupt change of texture, you have we can observe a similar thing. So it starts to stay on the sand layer. And the reason is now you have those capillary forces on top of the sand. So the sand has those big openings, but the clay layer doesn't want to give up the water. It wants to keep the water. That's actually a phenomenon that many golf courses use when they have a pretty sandy topsoil, and under that they actually have a much more coarser soil that drains even much more, because they want that on one hand the water drains quite well, but then they want also that it's not they want it drains quite well so people can play on that golf course quite quickly after a rain. But on the other hand, they still need some water that stays in that rooting zone, so the plants have something to drink. And then now 2 potentials. So we have now, to repeat that, we have that gravity potential that pulls it down. Now we have that metric, or this the capillary forces that pull it out to all sides toward the surface matrix of the soil. Now we have 2 more forces. One is that osmotic potential, and I will not really dwell too long on those forces. But the osmotic potential is actually quite important when it comes to the very last step of water entering roots. And in principle is, just imagine you have a container of water, and there it's separated with a small wall, a membrane that allows only water to pass. So on one side you have a high concentration of a salt, on the other side a lower concentration. Now the water wants to dilute that. So in this case, the water would move from the left side to the right side, because the water has that tendency, well, to dilute higher concentration liquids. And that is actually what happens in the soil. You have, if you have a good soil with low salinity, well, the water can actually be pulled into the plant where there is a higher salinity. So there you have the potassiums and the magnesiums and so other cations inside the plant, and it pulls the water for the very last nanometers, if you want, between the soil matrix and the root into the hairs of the root hairs. Whereas in a saline soil, well, there is a problem. Now you have sometimes a higher concentration outside than you have inside the roots, and that pulls the water out, or makes it at least very difficult for the plant actually to acquire the water. And the final one, just to make it complete, is the hydrostatical potential. And this is when you actually have your soil is more or less under the water table. That doesn't happen very often. It may occur if you, for example, if you have soil in a depression and there is seepage coming from left and right. That is where you have potential that actually pushes the water towards the water table. But that is something really much more very unlikely to happen in the soil environment. Well, let's have a look now, a little closer look to see what this actually means for the water that plants can actually use. So let's have a look at a soil particle. So around the soil particle, we have hygroscopic water. That is water that is actually so intimately entrenched with the soil particle, it's impossible to take it out. Sometimes it's actually in the matrix of the minerals. So that is the hygroscopic water. Around that is a circle, and this is called the adhesion water. You recall the first slide, adhesion and coadhesion water. That's the water that adheres to the surfaces. Well, the next one is that cohesion water. That is now water that adheres to other water, but still, if you want, along the whole way, there is some strength keeping everything together, but this strength of keeping the water to the soil surface gets less and less the further you go away from soil particles, or the more and more you go into larger pores. Now, that adhesion water and the cohesion water together is the capillary water. And the water that is outside in much larger pores, that is gravitational water. And that gravitational water is actually for the plants more or less useless. It runs through the soil and can't really be taken up by the plants. Now, once the soil dries out, there is still water kept back in the soil. It's exactly that capillary water that's kept to the soil surface. And when the soil reaches that point, we say at that point, the water is now held at field capacity. So that water won't drain, but it will remain in the soil. Now, when the soil keeps on drying out, well, it's getting more and more difficult for plants to extract that. And there comes a point where it is almost impossible for a plant to extract that. So the power that the plant has through transpiration is too much for the plant. It can't get it out. And that's when we say water is held at a permanent building point. So the water that can actually be used by the plant is what is in between. That's the plant available water. And these are very important principles. So the field capacity is a very useful parameter. So, but per definition, field capacity is the water that's held back after 72 hours of drainage. But basically what it means, that's the maximum amount of water can actually hold back after drainage. And why is this important? Well, one reason is it's that optimum where you have sufficient pore space to allow aeration for the roots to grow and for microorganisms. But at the same time, you have also enough water. Because let's face it, it's not only about bringing enough water to the plant. All those microorganisms inside your soil, they are actually aquatic. Many of them are aquatic microorganisms that live in this water. And this is a reason why when you send in a soil sample and you air dry it, many of those microorganisms stop functioning. They kind of get in a dormancy, if you want, in a dry dormancy, and they won't further break down some of those nutrients that would otherwise give you a false result in your soil sample that you submit. So this is it's an important criteria, the field capacity. And another reason is field capacity is often the point where you have a very easy tillage of your soil, if you till. And if you have a water content slightly higher than the field capacity, your soil becomes more it becomes more putty-like material and turns into mud. But slightly below the field capacity is oftentimes the best water content to work on your soil. Now the other one, and this field capacity, maybe just to mention that, I see that is something like between 70 to 300 hectopascal. That might not mean a lot for you. It's basically something like 6 to 7% of the car pressure of ordinary passenger car, and that maybe gives a better picture. Now the permanent building point is now the soil is dried out at the point that plants are basically unable to recover, and that force that holds the water back is about 6 to 7 times the average tire pressure of a passenger car. So that are a lot of forces, and everything in between. This difference is the water that plants can actually use. Now keep in mind, we say wilting point, but in reality, especially if you grow for crop production, the stress and a yield depression already starts quite earlier. Now, here is a point I want to make really sure that you understand. There is a really huge difference between water content, the absolute water content that you measure, and actually your water potential. And perhaps that's something that came out in the previous slides. The water potential is actually much more important for your plants. This is really the water that is available, that can be moved around. So you have maybe a soil that has a lot of water, like many fine textured soils, but that water is not very usable for the plants. And I'll get to that in detail a little bit further on with my slides. So you can convert one into the other, and I won't dwell too much on that. That's been used when you have certain instruments that you use for measuring the water content. And they look pretty characteristic for each single soil. You basically have your own curve that converts one into the other. For clay, for example, is a curve where you have to put a lot of pressure on the soil to get the water out. So it's a very slow curve if you want. Whereas when you have something like a silt, you release in the beginning a lot of water, and later on it slows down. So those curves that relate one into the other are very site-specific connection or a relationship. Now, what soil properties affect actually the water entry, movement, retention? So we talked about previously we talked about the forces, but what soil properties do actually affect those forces? And I think, yeah, I have a small breakout room, so I propose we'll take a 2-3 minutes break. It allows you to do other things. We can create a breakout room, or you just try to think for a minute, maybe write it down on a piece of paper. What forces do you think are actually, or let's say, influence or impact those forces in the soil? So I got here 6:35. Let's say I'll give you some 3-4 minutes. Let's go back 6:38. I have a lot of slides, and then see whether we can answer those questions together. Okay, so the question was before the break is, what are actually the soil properties, and is there any room that we can influence or help to improve those soil properties that actually affect those forces? And well, I begin maybe with one parameter that we cannot influence in most cases, and that is soil texture. And just as a fresh up, I think most of you are familiar with soil texture. When we talk about soil texture, We talk about all those small particles that are smaller than 2 millimeters. And everything above that, well, there is not much water in stones. They do contribute to your infiltration, but yeah, when we talk about soil texture, we think about actually in at least in agricultural terms of everything smaller than 2 millimeters, of mineral parts smaller than 2 millimeters. And accordingly, soil texture is defined by 3 separate classes. One is clay, one is silt, and one is sand. And according to that balance, we determine now, give it a name. And I give you an example. Let's say we have clay content of 20%, silt content of 40%, and the sand content again for 40%. Then we could look in something which is called soil texture triangle. Look at where clay is at 20%, whereas the silt, and that's at 40%. Hypothetically, we don't even need a third part now. Two components we have already altogether. They have to make to 100%. But anyways, I do it here, and we see in this case we have a loam. Now, it's much quicker sometimes just to go do it with your fingers. And there is a sheet, and I'm more than willing to forward you to the link that I use oftentimes. You can use the soil texture. You can determine it by the field method, because you don't, these days, not many people send in their soil samples for texture analysis. And your hand is oftentimes just as good as the lab result. Now, there is something interesting about the soil texture. Now, or soil texture and the plant available water. So when you look at the different texture classes, starting with sand, which has a lot of large pores, but those large pores don't retain much water. It drains real quick. But as it becomes finer, that field capacity, so the capacity to retain the water, gets more and more. And it levels out somewhere at the silt loam level. So something like medium coarse to slightly fine textured soil. Now the building coefficient, or the point where the water is retained at the permanent building point, that also increases from sand to the finer material, but that is more linear. So it's getting more and more, so that at the end, the optimum for when it comes to plant available water is around a silt loam material. So silt loam, that class separate, retains most of the plant available water. Again, that's not necessarily the most water it can be retained, but the most plant available water that is retained in that fraction, that loam silt loam fraction. So texture is one of the components or that influences the plant available water. As an example here, for example, this gives you an idea how much water is actually in the soil depending on what you have. And I prepared here that soil sample of a clay loam, right? So that clay loam has, according to that table here, for every centimeter you go down in the soil, it can contain about 1.5 millimeter of water. That's 1.5 liter on a square meter it can retain, which is available for water for every centimeter you go down in the soil. Now, if you go down 30 centimeter in the soil, well, that means actually now you have 45 millimeter of water available for the plants. That's 45 liter of water for the plants. Now, if you think that a plant is evaporating or transpiring, I would say something like 4 millimeter per day, it can hold you until the plant dies, basically 10 days. Now, we don't want, of course, that the plant dies, and yield reduction is oftentimes already at 30%. So you can hold with that water that's in the soil on a dry day without rain, you can easily hold 3 to 4 days before you have to start irrigation and before you notice actually yield reduction. Now, another part, and perhaps looking at the picture, you already have an idea where I'm driving at. So what you see here, well, this is the same field. That's the same field. On the right side, that is out of the ruts, of the tire ruts. And the left side, well, that's in the field itself. Well, you can imagine that water has some issues entering the right side, right? So we come now to what is called the soil structure, and we typically divide that in different categories. So we have that granular structure, or first of all, the single grain structure. These are the sands, and so where we really see the single grains. Well, not much farming going oftentimes on those soil, but what we find quite often in the topsoil is the granule, those round pearls, if you want, of soil. That is quite frequent, or at least that's something we want to see. In the subsoil, so a few centimeters below that, we find different expression of those aggregates. One very frequently encountered is the blocky one, so the blocky structure. Another one, so here you have a larger, if you want, larger units than those granulars, and oftentimes more angular than those round granular. It's a very frequent one you find in the subsoil. Those prismatic ones that are much longer in the depth than they're wide, you find them oftentimes when you have a lot of clay. So you have a shrink swell behavior that oftentimes causes those cracks, and it's also sometimes a impression of a high salt content. The disadvantage of those you have when you have a big crack, you have what is called a preferential flow, and the water can sometimes rush through that without actually entering those aggregates. Then we have those platy structure that's on the bottom left, and that is sometimes inherited from the parent material, but sometimes it can also be the result of nutrient and organic matter loss or compaction. So if it's not from parent material, it's oftentimes a warning sign if you see that. And finally, massive, that can be also natural or from compaction. So here you don't see much structure, it's just one massive block. So the impact of the soil structure, well, we saw is definitely, first of all, it's the flow itself, but it's much more actually. When you have a good soil structure, you also have good root growth. And with a good root growth, you also have stronger roots, and they can extract much more water. Another thing that's perhaps not so evident is those aggregates also protect the organic matter inside. And this organic matter, we'll get to that later on, is actually one way of increasing your retention capacity. So what is actually soil structure here? So it's an aggregation of soil particles. And when you go from, let's say here, from the right to the left, you have the smallest aggregates. And here at that level, what kind of keeps them together are things like organic polymers or aluminum oxides. And at the very small level, on the clay particle level, there's sometimes the attraction of charges between those clay particles. Now, that is sometimes quite important when you have a lot of sodium in the soil, because that sodium goes between those clay particles and disperses them. And that destroys, especially on the surface, the soil structure and makes the entrance of water impossible or difficult. Larger particles then, as it becomes bigger and bigger, they still have microbial gum that keeps it together, but now fungal hyphae and root hairs keeping it together. There are also, of course, other more physical phenomena other than those biological phenomena, which is the wetting and drying circles or swelling and shrinking of clay particles that also contribute to soil structure. Many of those influences are hard to manipulate from our end. So what are actually the signs of good soil structure? Yeah. Again, I'll give you, we don't have to go now, or yeah, let's make another 3-4 minutes. What are actually the signs of a good soil structure? What do you think qualifies for good soil structure, and what makes structure less desirable? So before our breakout, we said about the importance of structure for soil, for roots to get actually soil water. And soil structure, as opposed to texture is something we can actually influence, and I'll get to that later. Again, soil structure is, it not only dictates the way water flows in the soil, how it penetrates into the surface, and but also how it infiltrates into the surface and percolates inside the soil profile, but also the way the pores are distributed and allowing plant roots to grow and have that gas exchange that's necessary for respiration. So what is now a sign of a good soil structure? Let's see. Okay, so in what we often see at the topsoil, if at least in some grasslands, it's well managed, we find a good aggregation on the topsoil. And this crumbly soil with water stable granules, and I'll get to that what actually water stable means. That on one hand don't disintegrate easily, but on the other hand they're strong enough, let's say, to resist water and precipitation. So that is oftentimes something we like to see, but of course, the further we go down in the soil, that is more something we don't actually find. Now, I'll make that a poll, so just to show you that it's actually much more tricky than just having that black crumbly. So do you think actually, now that's from a subsoil, and this is actually relatively silty, loam silty material. And I just want to get your opinion. Do you think that is actually a bad or a good soil structure? And I have a poll, if you can pull that up. Okay, I think when you look at that picture, of course, in the beginning, I think I understand why many people choose to say that looks pretty bad. How do the roots actually penetrate that? But if you look closer, you see those pores. And actually, when you pull that apart, it's pretty easy. So roots can penetrate that part. And that structure, although it's a massive soil structure, it's actually not that shabby, right? You see there is actually life, and once you, or when I took that apart, you saw actually there is life inside. So there is aeration, and actually it can retain quite a lot of water. It's a silt loam structure. So it's a subsoil, there's not much organic, but still when it comes to water retention, it's not that bad, right? So you see actually, it's not so easy to answer here. You see here a blocky structure. On one hand is that angular structure that is a sign of high clay content. And on the left side, you have that subangular blocky. So what is it good or bad, right? It's not easy to say. It depends actually more on how strong those aggregates keep together and how big they are. We basically need to put ourselves in the shoes of the roots, and then see how easily actually can they penetrate those aggregates. There are different ways we can measure that, and here is something I think Serena can talk to a lot. There is, for example, the USD NRCS soil quality test kit, and I think the BC Forage Council actually owns a few of them. You can measure two things with that kit: the aggregate stability. Basically, what you do is you test the water and the resistance to flowing water. You take, after some pre-treatments, you take some wet soil aggregates and dip them several times into water and see how many actually of those aggregates are still connected or kept together. The slake test is a little bit different. It's a different angle. That's not so much a resistance of water that attacks from outside. That's more if water starts, if the if it wets, and then how stable actually aggregates are when it comes to rapid wetting. And that is more caused by the different swelling of the clays and of entrapped air. So it's a little bit different. It's both aggregate stability, but it's not necessary that aggregates that are stable from the outside are actually stable from the inside. So those are different components. But you can also go a much quicker way, and that's a field method. So basically, you take a spade of your soil. You do that, of course, when the soil is not absolutely bone dry or when it's overly wet. So again, it's field capacity. It's been drained, so it's moist. You take some of that soil, hip high approximately, and a hard surface, plywood board or something, and let it drop once, maybe twice, at most 3 times, but it shouldn't be much more. And then you start to sort them, the bigger aggregates to one side, the finer to the other side, and then compare it to something like that. So ideally, you want to have something like on the left side. You don't want to have enough clogging. So it should break at that. It should have enough resistance. It doesn't break right away, but it does break when you let it fall something like 2 feet, from 2 feet high. After a while, it should break up. That is a real quick field methods. But once you do go down on that plywood core and you take them a little bit more apart, you also want to look on signs like color or roots or smell, right? Does it smell, for example, does it really smell earth, or is there some other smell that is more like cabbage or so, which shows a sign of anaerobic, means there is not much air in your soil, not much more air exchange. Or you press them together, how easily do they break, those aggregates? What you don't see with those tests, they are oftentimes from the top foot at most, is of course if you have impermeable layer inside the profile, and that here the only way basically to look once in a while is having a salt pit, or you dig all the way down and let's say 2-3 feet, then you can actually see whether you have something like, in this case, a plow pan. So you see that the roots stop growing somewhere at 20 centimeters from the top, and that is something you don't necessarily see with those tests I showed you. A warning sign is also for bad soil structure is if you have still a residue that is not decomposed after in the next year when you start the season, if it's around, that means there's not much air coming inside the soil. Something else that can happen, and that is more now why it's actually important to keep your soil vegetated, is when the soil is not protected, those raindrops start to destroy the surface, right? And then it starts to dislodge those soil particles, and they block the pores. And with time, that water runs off or can't really penetrate your soil. And I show you something that is also a real life picture. If you want, here you see that sealing layer, and well, this is what happened, right? This part, it was tilt, basically, very aggressively tilt the surface to make it even, but in the end, the opposite was achieved, right? And you see that air can't really penetrate in the soil. You see on the right side, that color, that bluish color shows that there is not really air inside the soil. And on the left side, you see corn, and it has actually deficiency of phosphorus deficiency, which is caused by a slow or not existing root growth, and it can't access the phosphorus. Now, last but not least, one of the factors is actually soil biota and organic matter. And here is definitely something we can do a lot. Well, one very obvious picture. So this, while you have those earthworm pores and water, this is water that has been dyed, and you see how it runs down those pores. Now the fluoropores and those macropores is much faster than, of course, in the matrix around. So it reaches there, it goes into the soil. If it's extreme, of course, it's maybe too fast and you lose some, but all in all, it's definitely something you want to see. Now, don't get frustrated if you don't have earthworms, because that's just a geohistorical thing here in BC. After the Ice Age, they were all kind of killed, if you want, and they start to come back. And many of the earthworms you actually see in the fields have been introduced either intentionally or unintentionally by growers and people who settled inside or started farming. But you have other organisms that can take over. But this is a pretty striking picture, of course, of the importance of life in the soil. Then fungi. This is, you saw here on this picture, you know, on the left side, fungi are present, right? And fungi work on two levels, if you want. One is the exudates, the school, and that is, they have in common that with other microorganisms, that microbial goo. And then you have the hyphae, those threads of the fungi, if you want, the roots of the fungi that keep those granules together. A very important thing that's actually only recently discovered is a glucoprotein called glomalin. So what you see here are the hyphae of a avascular mycorrhizae. So avascular mycorrhizae are symbiosis of a fungus with certain plants. And what you see here is the green color that's actually has dyed, that's done in the lab. Normally that glucoprotein is actually brown. When you dye that, it becomes green, or with this certain dye, it becomes green. Now, this glomalin is pretty heat resistant and is resistant to, it does not dissolve easily in water, and so it's actually, and it's pretty tough, and it's ideal if you want storage of carbon. And we know by now that in undisturbed soils, in areas where you do have that mycorrhizae, at least 20% is actually in form of glomalin in the soil. Now, most plants, 80% of all the land plants, do have a symbiosis, if you allow, with glomalin, sorry, with those mycorrhizae. It's actually one family of mushrooms, of fungi, which are the glomerulomycota. But there are a few ones that don't have those mycorrhizal relationships. And just to give you an example of the, let's say, of those, some crops with agriculture importance are the brassica, for example, the mustard family, does not have a symbiosis with mycorrhizae or avascular mycorrhizae. And in the amaranth family, that is spinach or beet, sugar beet, for example, doesn't have. And in the legume family, it is just known for the lupine, so we don't use that a lot in forage anyways. But that's the only one where we know it does not have a mycorrhizal symbiosis. Buckwheat, rhubarb, for example, and the daisy family, sunflower, artichokes, but these are the exception. Again, 80%, most grasses and so on do have that relationship. And of course, here you see another picture. You see how important that is. On the left side, you don't see any organic. It's the same field, the same texture. And on the right side, you see the organic matter, how it's become granular, and on the left side it's just depleted of organic matter. Now, one thing is this organic matter. We kind of, I stressed a little bit the hyphae that keep us together, but also, well, in this case the glomalin, but there's fungal or microbial glue that keeps the aggregate together. But there is another point to organic matter itself. It itself has a water retention capacity, and well, it does, so that when you increase the water, the organic matter content in your soil, you do increase the field capacity. Relatively, it's a relatively steep connection. You do also increase the permanent wilting point. But you see from that curve, one is steep, the other one is a little bit more flat, that actually you gain, right? You gain on plant available water when you increase the water content. Now, just again, to make it a little bit more interactive here, I just want you to, can you pull up the next, I want you to guess how much water actually can be stored by, when we increase our soil, the soil organic matter content by 1% in soil organic matter. Is it 5 gallons per acre? Is it 8, 15, 20? So, well, if you increase the organic matter in the soil, we can kind of get an additional 25,000 gallons. It shows here. The number is probably a little bit high. That's from the USDA. That's one ad they had, I don't know, a couple of years ago for secrets of soil and soil health. It's probably more the estimates, they range somewhere from north of 16,000 gallons to 20,000 gallons. But let's say it's 20,000 gallons. That would be an additional 18 millimeter of water, or if you want that in 18 liters per square meter. That keeps, well, that replaces 2 good showers inside during the summertime, right? That you can retain with soil organic matter. Now, maybe one important thing is that not all organic matter is the same. And you know that, for example, peat can hold a lot of water, but then it quickly releases that. Now, when you have bark, like pine bark or other bark, it holds much less water, but once the water is inside, it dries much slower than peat. And another example here is, for example, when you take organic salts. Now, going from the right to the left, so fibric salts are material that is less decomposed, weakly decomposed material. And those humic salts, they are on the left side, they are more decomposed. And what you see, those fibric salt, those fibrous salt, less decomposed salts, they are can hold much more water, but they also release water much more quickly. Whereas that more decomposed material is the total amount it can retain is not as much as the fibric, but it retains it for much longer. So it needs much more power. So you do have a much better storage here. And actually, just talking about that, this is a reason why the mushroom industry, for example, use that more decomposed material as casing for their production, because it stays longer dry. Whereas the fibrous material that is sometimes used in horticulture drains much quicker and needs to be watered more often. To apply that now back to our soils, well, I don't, this is not the purpose of this presentation to talk about the soil, of the carbon cycle in the soil, but there's a few things I want to point out. So when we look at the soil, we roughly differentiate between 2 pools. One is the active carbon pool and the other one is the passive pool. So the active pool is basically the material, the litter or that soil amendment you put on the soil, and that feeds the microorganisms. That keeps them alive, and that is important for the soil structure because it feeds those microorganisms that produce that gum, that produce the hyphae, and that keep that structure in place. But most of that is actually returned back into the atmosphere as carbon dioxide. It goes in and loses. Globally, I saw numbers that actually only 10 to 50% of that material that's applied is actually stays in the soil. This is where now the passive pool comes in. And of course, that's pretty simplified now. There is different grades, but passive pool doesn't mean these are recalcitrant materials. That just means they are more protected, either in combination with a clay mineral or because they are protected in a structure, in a soil aggregate. Here again, the importance of soil aggregate. But now this passive pool, those very highly decomposed material and restructured and reformed polymers, they have actually high capacity to retain water. And now you see actually the beauty of how it works together. This active pool creates the aggregate that protects actually this passive pool, which can retain a lot of water. The structure, the active pool brings in the air, the passive pool retains the water. So we have basically now that feeds the bugs, and that actually is important to retain the water. And the passive pool is important when you really have a dry period, because now this is the water that's retained in the soil. And while the bugs don't move anymore, but you still actually have some water in the soil. The organic material on top also improves the infiltration. You see on the left side that is some straw material that's been applied, and you see how infiltration through that biology activity is actually improved. And of course, you need the water enters the soil so it can be stored. Now, all those factors, of course, they are not even. You have heterogeneous soils, and what can also happen now, you have that movement which is not even. And there is another phenomena that occurs, which is called, when it comes to an extreme, this is the preferential flow. This can happen as a result of major biopores, pathogenic cracks like shrink and swell of clays, freezing and thawing. Or sometimes they're hydrophobic organic coatings on grains and aggregates. So this is why our flow, and I think Mike will talk about that a bit more about infiltration, is oftentimes not just a simple addition of different properties, but sometimes the water may thicker or much slower infiltrate in the soil. Something that unfortunately happens a lot is heating and fire on top. And what happens when there's fire on top, it distills the organic components that condense then on the surface of those grains, and that makes them actually hydrophobic. So dry organic matter, and especially when it's been heated, actually repels water, and which can cause erosion. Now, where do the plants come in? And well, transpire, and per se, we said, well, 50 to 60%, I said in the beginning, is actually reaching the plant. And well, they suck all the water out. And actually, plants are pretty inefficient. Only out of that 50, 60%, out of that, oftentimes only 2% is actually used inside the plant, either in the vacuoles or to produce sugars. The rest is basically just going in the air. And the more water you actually offer the plant, plants tend to have what is called a luxury consumption. They actually try to drink all the water. When they get it, they drink it. They're not necessarily very efficient. Now, what happens now when the soil dries out? Well, then there are two things that actually happen. First of all, you don't have the water anymore to maintain that turgor, that pressure on the cells. So they get kind of those, the leaves they crumble and the stems become weak. But another thing is that now, well, on the right side, you see actually this is a leaf, the vein of a corn leaf cut, and what you see where I have the carbon dioxide and the water, these are stomata. These are pores on top of, and sometimes in the bottom here and in corn, of leaves. And when it's not enough water, they close. And when they close, then, well, water, they don't lose water, but on the other hand, carbon dioxide can't get in. And carbon dioxide is needed to actually create sugar. Now, when there's no sugar build anymore, well, the plants start to work on their reserves, and they start to be counterproductive. They're building down, they're exploiting their own reserves. So it actually is a double whammy, if you want, if there is a drought happening. Now, some plants, those plants that are coming from more arid areas, have developed some tricks. And I'm referring here to what are called the C4 plants, like corn, but it's also sorghum, and sugarcane is actually a very efficient user of water. But those plants have a trick. They are able actually to intermediately store this carbon dioxide. Then when you close the stomata, and either in the night or because of heat, they can release it. So they have a little more leeway, if you want, in producing sugars. But anyways, even if it is very dry, even those plants at one point will basically have to give up. Now, of course, we have the plants, they're respire, but on the other hand, that's a loss to the soil, if you want, that consumption. But there are also other advantages. After a while, plants start to shade either by the canopy or by residues, shade the ground, reducing the evaporation from the soil. Another advantage is actually looking here at that what is called a a rain simulator, is the effect of plants on runoff, also on infiltration. You see on the left side, there is just applied, there is no plant growing on those two, there's just organic material applied to the ground, but no plants growing. Now the plants, on the right side, you see how there's much less water actually run off from the surface of the soil, and this water has infiltrated in the soil. So plants do contribute not only by their organic matter they provide through the roots. And maybe something I haven't really mentioned yet, stress is that many of those root exudates actually are very important to support microbial life and then soil structure. But at the same time, these are oftentimes those carbons that stay in the soil. What is of course also important is that you have the diversity of different plants that root in different depths and explore different layers of the soil. And if you compare that, actually, if you're a little bit familiar with the principle of regenerative agriculture, what you actually achieve with just having cover crops is 3 of those principles. You keep the soil surface covered, you keep the roots inside the soil and living roots, and you grow. And when you grow a diverse range of crops, you, by the different growing pattern, you do develop a totally different structure than when you have a monoculture. Now, how do plants actually take up water? So the actual part where the plants take up the water is a very small part of the roots on the tip and on the little hairs behind the tip. And when it dries out, they kind of retract and leave a big crack and can't actually get the water out. Now, if you actually analyze that really carefully, or people have done that, probably you definitely don't have the time, nor do I, but they found out that actually only 1% of the total soil particle surface is covered by roots. Now, that's not a lot. This is where, again, the mycorrhiza come in. Mycorrhiza have a much finer roots. That's just a fraction of the size even of root hairs. They can penetrate much smaller pores, but they are also much denser. And these tubes, if you want, those water lines are very important also to survive in drought. And how do you get them? Well, again, the same, you need to feed them, right? You make sure that the soil stays relatively undisturbed, you don't cut them, and that you keep on feeding them. Now, when you look at the rooting depth of soil, typically most of the water is actually coming only from the top 30 centimeter. In this case, actually, you see for photo radish, they found that 70% or 68% came from the top 20 centimeter. Here for Phacelia and cover crop, it was 70% in first 20 centimeter, and lupine, it was almost 90%. Now, in corn, it's probably 40% is coming from the top food, another 30% from the next food, and 20% from the next. But this, and grapes and fruit trees and so on, they are, of course, go a little bit deeper. They stay longer, and they are able to extract water from deeper horizons. Now, plants are perhaps not so much different to, in many points, to us humans. So if the water is there, they stay in that 30 centimeter. And they start to explore lower layers only if they have to. But that doesn't happen overnight. So they must be trained. And that is, for example, if you apply water, not every day, but let's say less frequent, but more. So the water infiltrates more in the soil and forces actually the roots to explore deeper depths. That is actually also another thing that's interesting. Plants can also redistribute actually the water inside the soil. So they grow when they grow in an area where there is a lot of water, they are actually able to lift it into areas where there's less water. And you see that on an ecological level in certain parts, even in BC. Although this is a picture that is not from BC, where you see sagebrush growing together with crested wheatgrass. The hydrological balance doesn't allow for the crested wheatgrass to grow there, and people were wondering why that happens until they found out it's actually the sagebrush that lifted the water to the surface, allowing the crested wheatgrass to grow. Now, maybe I'm getting now towards the end of the presentation. There's another thing when where the crop growth can be influenced by our doing, or the root growth. And I refer here to a classic trial done by a gentleman called Drew in 1975 in the UK. So what he did, he basically provided localized supply of nutrients, and then investigated how does that show with the root growth. He used barley in that case. So he provided, you see there's different layers, he provided the nutrients at different levels in the root, and then and always, well, what he did, he then took out one nutrient in each layer. For example, he took provide only very little to the top, very little nitrogen to the bottom, but a lot nitrogen in the middle, while all the other nutrients were just sufficiently supplied. And well, I'm just giving you the result. This is the way it results. So the control got all the nutrients together. Now, when he provided almost no nutrients on the top and no nutrients in the bottom, but in the middle he provided the phosphorus, you see how the roots actually started to grow quite strongly there, and compensated basically for the lack of nutrients in the upper and lower part of the rooting zones. The absolute root length was not so much impacted. It was pretty similar. And the same we observed with nitrate. Now I have to say this has been observed with many other plants, and not so strong when it comes to corn. In barley, as you see, that is barley. It was pretty extreme. Some grasses do react quite strongly on that phenomena. But what it teaches us is that the way the nutrients are distributed in the soil do also contribute, and the way we fertilize do also contribute to the way the roots grow and explore the soil. And as a general, this is basically a summary of different publications, if you want, on nitrogen supply and root growth. And you see the more you supply, the more actually the plants start to stay on top, because while it's supplied to the top, and if they are forced to supply in the bottom, you probably lose some of the biomass because you can't grow. But when it comes then to a drought, those plants, the one in the middle or the ones to the left, well, that is probably a little bit meager, but the two in the middle, they will probably at least produce something, while the one to the right will probably dry. So that is basically maybe that leaves me, I think that is pretty much the last slide. When we talk about soil management for drought resilience, kind of summarizing what we saw on the slides before, we need, of course, to bring the water into the soil first, and that can be done by residues, cover crops, and low impact tillage. Now, to increase the water retention, again, add organic matter, but don't be frustrated if, well, the water retention per se does not increase so quickly, because, well, it needs some time to build up that passive pool. Slow down evaporation. Well, again, we can, that where the plants coming leave residues, that slows down the evaporation. Rooting depth, too, we can actually impact the rooting depth and efficiency of roots by smart irrigation, by smart application of nutrients to the soil. Now, I might be here maybe provide a little bit, let's say, a opinion that may not be shared with everybody, but I think it won't hurt when you see a stratification of your soil after a while. Where that can happen when you have no tillage. When you see stratification of the soil with time, you may perhaps need to do a soil pit and do some more intensive sampling. That once every couple of years, and I don't talk every year, absolutely not, but maybe every 4 or 5 years, that you disc a little bit deeper, just to make sure that those nutrients don't stay all in the same place. And again, basically what we covered here, maybe except for keep the soil undisturbed, and that doesn't mean that, it means in principle, yes, undisturbed, but it doesn't mean that, well, you may reconsider after a couple of years to do a little bit scratching to make sure those nutrients are available for the whole root zone. But other than that, you have basically, when you observe the principle of regenerative agriculture, you're pretty much on the track to have more drought-resistant plants. And I think that's pretty much what I had to show for that evening. Well, I thank you for your patience. I hope there weren't too many slides. I was once told when you show more than 18 slides per second, you have a movie. I hope that was not the case here, and hopefully you got a little bit out of those presentations, or at least material to ponder about. And here's my email address, so I'm open to answer questions. That depends on how much time we have, but I'm also, you can reach out to me anytime. And if you can't read that or don't have anything to write down, Serena can provide you with my contact information. Thank you very much.